Bismillahirrahmanirrahim. In this session, we will discuss about the musical notes produced in songs, and we will discuss this under the subject of physics O level uh, from the book written by Tom Duncan and Heather Kennett and published by Hodder's Education. Uh, some irregular vibrations, such as those of motor engines, cause noise. So, motor noise creates noise because of regular vibrations, such as occur in instrument of brass band produce musical notes. So, irregular vibration cause noises. So, the irregular vibration that produced by the motor engines cause noise, but regular vibrations such as occur in instrument of brass band produce musical notes. So regular vibration is melodious, is a musical note, and which has three properties. So this has three properties: pitch, loudness, and quality. Pitch of a note depends on the frequency of the sound wave. Pitch of a note, musical note, depends on the frequency of the sound wave reaching the air, on the frequency of the source of the sound. A high pitch note has a high frequency. If the high pitch note is there, the high frequency is there and a short wavelength. The frequency of middle C is 256 vibration per second or 256 hertz, and that of the upper C is 512 hertz. Note or octave part of the frequency of one is twice that of the other. The pitch is like color in light, both depends on the frequency. Notes of known frequency can be produced in the laboratory by a signal generator supplying alternating electric current to a loudspeaker. The cone of the speaker vibrates at the frequency of AC, which can be varied and read off a scale on the generator. A set of tuning forks with frequencies marked on them can also be used. So, this tuning fork generates single type of frequency. The tuning fork has two steel prongs. These are the prongs which vibrate when struck. When struck to a material, any material, the prongs move in and out together like this, generating compression and rarefaction. So this causes a vibration of frequencies in note loudness, the pitch as a frequency. So this can pitch and frequencies can be produced using different kind of instrument, and for this purpose this tuning fork can also be used, and it produces a singular frequencies. Loudness, a note becomes louder. A musical note becomes louder when more sound energy enters our ears per second than before. If more energy reaches to our ear, then it means the loudness is higher. This will happen when the source is vibrating with a larger magnitude. When a source is vibrating with a higher amplitude, then loudness will be higher. If a violin string is bowed more strongly, its amplitude of vibration increases, as does that of the resulting sound, and the note here is louder because more energy has been used to produce it. When more energies are used, then loudness will be higher because more amplitude will be there and more loudness will be high. Quality, the same note on a different instrument sounds different. Notes are same, the frequencies are same on a different instrument sounds different. We say that the notes differ in quality or timbre. So same instrument on different instruments sounds different. Same notes on a different instruments generate different quality. The difference arises because no instrument except a tuning fork and a signal generator emits a pure note. Only tuning fork and signal generator emits pure note or one frequency note. Others creates a combination of frequencies of sounds. So the wavelength of a note playing near a microphone connected to a CRT oscilloscope can be displayed on the CRO screen is this. Uh, those from the same note on three instruments are shown in figure. A tuning fork, a pure sinusoidal waves is produced. A piano, here we see that some kind of noise added here. The frequencies is almost the same here and then here. This is piano, this is violin, this is pure sine waves from a tuning fork. This and this contains some different subharmonics, harmonics, which creates different notes. So this have a different quality. Although they have the same frequencies, the repetition time is same, the period is same. So, but their subharmonics, harmonics are different than this piano. So, although the pitch are same, note that the same frequencies but different quality. The qualities are different. So the qualities are different because the other harmonics are different. No harmonics here, but here we have different harmonics. Here we have no harmonics. It's a pure sinusoidal wave. Their different shapes show that while they have the same fundamental frequency, they differ, quality differ because they contain additional frequencies. Harmonics is the additional frequencies are harmonics. And the pure note of tuning fork has a sine wave and a simple kind of sound waves. Note that although the wave on the CRO screen is transverse, it represents a longitudinal sound waves. Some of the questions from practice sessions. If the frequency of upper C is 512 Hz, the speed of the sound is air is 340 meters per second. Calculate the wavelength in air. So this is frequency 512 Hz and speed of sound is 340 meters per second lambda. So V is equal to lambda F, lambda is equal to V upon F, 340 meters per second, and frequency of upper C is 512. So the frequency of middle C will be 256. So middle C is used. So we have to calculate for the middle C. So that's 1. That's why the lambda is 1.328 meters. If the wavelength of the sound wave in air is 1 meter, taking the speed of the sound in air to be 340 meters per second, calculate the frequency of the sound. So lambda is 1 meters, V is equal to 340 meters per second. So frequency is V upon lambda is 340 Hertz. So the frequency is 340 Hertz. So overtones, we can see that this is middle C and this is upper C, double C. So in the next session we will discuss